Yes, welcome back to the next session of Design of Pre-Stressed Concrete Elements course. So in the last session, we were solving problems in connection with the stress concepts. So let us work out or proceed with a few more problems. Okay, or we will work out a few more problems today. So let me take the one more problem in the stress concept. An unsymmetrical I-section beam is used to support an imposed load of 2 kilonewton per meter over a span of 8 meter. The sectional details are top flange 300 millimeter wide and 60 mm thick, comma, bottom flange 100 mm wide and 60 mm thick. Okay, so this is clearly indicating that this is an unsymmetrical I section. So in the examination, instead of giving unsymmetrical I section, okay, directly they may give the sectional details. Okay, by reading the sectional details or by reading the dimension of the section, you need to identify that it is an unsymmetrical I section. Okay, so next, the thickness of the web is 80 millimeter, comma, overall depth of the beam 400 millimeter. I have taken the same dimensions which have been worked out in the last problem. At the quarter of the span, okay, at the quarter of the span, the effective pre-stressing force of 100 kilonewton is located at 50 mm from the soffit of the beam. At the quarter of the span, the effective pre-stressing force of 100 kilonewton is located at 50 mm from the soffit of the beam. Full stop. Estimate the stresses at the quarter of span section of the beam for the following conditions. I will repeat. Estimate the stresses at the quarter of a span section for the following condition or loading conditions. One is pre-stress plus self-weight or at transfer. And second one, pre-stress plus self-weight plus live load or at working. So as I stated, in the examination, they may ask pre-stress plus self-weight or they may ask at transfer condition. Okay, here also the same thing. They may ask pre-stress plus self-weight plus live load, or they can directly give at working condition. So this is the problem they have been given. The same problem we have been worked out in the last session. Okay, in the last session, okay, the same section and the same dimension have been considered. But in the last problem, we have been worked that problem for mid-span section. Now we are working the same problem for quarter of the span section. So that is the only change in the problem. Is it clear? So let me recapitulate, because since all the dimensions are same, okay, so let me proceed with the basics things which have been worked out. So now as I did, okay, so these are all the things. Okay, please write down the diagram. So as I stated, so the flange dimensions are 300 millimeter wide and 60 mm depth is the top flange width, and then the bottom flange is 100 millimeter wide and 60 mm thick, and the web dimension is 80 millimeter. Okay, overall depth of the section 400 millimeter, and the span is 8 meter with an imposed or live load of 2 kilonewton per meter. So these are all the dimensions they have been given. Is it clear? And one more thing, the pre-stressing force has been induced inside the section at a distance of 50 mm from the soffit of the beam. Okay. So now let me proceed with the problem. So as I stated, okay, so we need to, okay, first calculate or know whether the eccentricity, pre-stressing force, all those things are given. The same thing I'm going to work out here also. So let me go ahead with the pre-stressing force. So the pre-stressing force, they have been given in the problem, that is 100 kilonewton. The same thing I have been written here. Next, coming to the cross-sectional area or area of a cross-section. Now the cross-sectional area or the area of a cross-section is I section. So let me go ahead. So as I stated, so consider the top flange dimension whose width is 300 and depth is 60. 360 plus, okay, the web dimension 80 multiplied by 280. So as I stated, okay, so if I'm going to okay, deduct the overall depth minus this flange depth, that is 400 minus 120, you will get this dimension as 280. So this dimension is 280. So this dimension is 280. Okay. Next. Okay. So plus the last, that is the lower flange dimension, that is 100 multiplied by 60. 100 multiplied by 60. So which workouts to be 46400 millimeter square. Okay, 46400. So the area of a cross section is 46,400 millimeter square. So now next is, okay, centroidal distance of the section. Centroidal distance of this section. Okay, so we don't know the centroidal distance. So let me calculate that. So the same thing what I did was the same dimension. Now once again I'm going to do. So once again, if I want to calculate the centroidal distance, okay, so let me calculate either from the top or from the bottom. So let me calculate it from the top, hence I will write it as y top. Okay, and while calculating, always we need to keep the reference axis. So this will be your reference axis. Okay, so let me call it as RA. Okay, a reference axis. Okay, so this will be your reference axis. So you know the formula to calculate the centroidal distance, that is A1, area of the first section, multiplied by the centroidal distance of the first section measured from the reference axis, plus A2y2 A3y3 divided by A1 plus A2 plus A3. Same thing which have been worked out in the last. So let me substitute that. As I stated, 300 into 60. 300 into 60 is the first area, and the next, the centroidal distance, as I stated, is this one, that is centroidal distance of this is y1. Okay, so it is y1, so that distance is 30. So this they have been worked out in the last. The same thing I've been repeating here. Okay, next, the second dimension is 80 is the width and 280 is the depth. Okay, and the centroidal distance of this section is measured from the reference axis till here. So this will be your what I can say, the y2 distance. So this will be your y2. Okay, so therefore area 2 is 80 into 280 and the y2 is 60 plus 280 by 2, because you know this is a rectangle. 280 by 2 is the centroidal distance, so it should be measured from the reference axis, hence add this. Okay, that is plus 60. So once again, the third dimension is A300 into 60 multiplied by the, okay, the corresponding, the centroidal distance here also the same. Okay, so this will be the centroidal distance which I am going to measure. Okay, so this will be your y3. So this will be your y3. So that is 60 plus 280 plus 30. So which works out to be 370. So substitute that. Okay, divided by A1, you already know A2 and A3. So which works out to be the same thing, that is 156. Okay, the same problem we have been worked out in the last session. The same problem have been considered here also. The same section, the same dimension have been considered here. Okay, and eccentricity you already know that eccentricity is defined as it is the distance between where the pre-stressing force induced to the distance the centroidal of the axis of the section. Now you already know that. Okay, the distance of this is, okay, you already know, okay, that is 400 minus 50, that is 350. So okay, in 350, okay, deduct this 156 from the top, that is one, that is central distance from the top, you will get this eccentricity distance. Okay, so this will be your 350. So this will be your 350 millimeter. Okay, so this will be your 350 millimeter because they are being given the distance of pre-stressing force from the bottom is 50. So if you deduct the overall depth minus this soffit of the beam distance, so that is workouts to be 350. So which workouts to be 350. Okay, so this workouts to be 350. Okay, so therefore 350 minus this, okay, the distance which workouts to be, okay, 194 millimeter. So once again, you need to calculate the moment of area. So as I've discussed in the last class, same thing I've been repeating here. Okay, because I've been consider the same cross section, same dimension. That is the moment of inertia of the first section, moment of inertia of the second section, moment of inertia of the third section. So the formula is given by BD cube by 12, that is moment of inertia of the first section about the central axis, which is a rectangular section, hence it is BD cube by 12. Okay, plus area of the first section, that is 300 multiplied by 60 into y1, you already know, that is 30 minus 156 is the centroidal distance from the top whole square, like that, plus the second moment of inertia, okay, of the second section is, or moment of inertia of the second section is, okay, the second section is also a rectangle, you can see here. So hence 80 into 280 cube by 12 plus area of the second section 80 into 280, okay, multiply by 200, okay, y2 you already know, minus the same centroidal distance whole square. Next, the third section, that is 100 into 60 cube by 12, because it is a rectangular section, that is BD cube by 12. Okay, so same, okay, plus area of this 100 into 60 multiply by y3 370, which we have already been calculated, minus the yt or y top measure from the top. Okay, so which workouts to be 757.46 into 10 to the power of 6 millimeter to the power of 4. Okay, next, sectional modulus. Sectional modulus. Okay, the sectional modulus for this I section, okay, we are going to calculate like this. Zt is equal to moment of inertia of the section divided by the y top. Okay, so moment of inertia we've already been calculated about the central axis. The same thing I am going to substitute here, 757.46 into 10 to the power of 6 divided by the y top. Okay, so the y top we have already been calculated 156.03. So which workouts to be 4.854 into 10 to the power of 6 millimeter cube. So we need to be very careful regarding the units. So this is millimeter to the power of 4 and yt is in millimeter. So which workouts to be millimeter cube. Next, Z bottom. Okay, why? Because ZT and ZB are not same here. Why? Because it is not a symmetrical section. We need to calculate it separately. YT and YB are different. So how to calculate Y bottom? So Y bottom can be calculated from overall depth minus Y top. Overall depth minus Y top, that is 400 minus 156 something. So which workouts to be 243.96. Okay, so substitute this, you will get an answer of 3.10 into 10 to the power of 6 millimeter cube. Okay, so this is regarding the section modulus. Now comes the self weight of the beam. Okay, so the same thing here also we are going to do, that is cross-sectional area multiply by the density of a concrete. So we already been calculated the cross-sectional area, that is 46,400 millimeter square. Please note down while calculating the dead load. Be careful because we want the final answer in kilonewton per meter. So please be careful. Okay, hence 46,400 divided by 10 to the power of 6. Why 10 to the power of 6? Because we need to convert this millimeter square into meter square. So hence divided by 10 to the power of 6. So therefore 0.0464 into density of concrete is 24 kilonewton per meter cube, which works out to be this. 1.11 or 1.12. If you're going to round off, it will be 1.12 kilonewton per meter. So till this, okay, which we have been worked out. So now come to the actual scenario, and also the live load, okay, also been given in the problem, which is 2 kilonewton per meter. So now in the last problem, we used to calculate the dead load moment and live load moment, okay, by using a formula WL square by 8. Am I right? Okay, so we used to calculate the dead load and the live load moment by a formula, because you can see from the last problem, okay, we have been used the formula WL square by 8 for dead load moment and live load moment also WL square by 8. But coming to this problem, okay, we cannot use that formula because we are not calculating the stresses at mid-span section. We are calculating the stresses at quarter span section. So hence, let us proceed how to calculate the dead load moment at quarter span section. Because we are calculating the stresses at quarter span section, hence we need to calculate the dead load moment and live load moment, okay, also in, okay, quarter span section. So let me go ahead with the problem. So this is the, okay, the thing they have been given. Okay, so this is the beam, okay, which have been applied with a uniformly distributed load of 1.11 kilonewton per meter. Okay, 1.11 kilonewton per meter. Okay, so and the span is 8 meter. Okay, so please listen here carefully. So now I want to calculate, okay, the stresses at quarter span, hence I'm going to consider or calculate the, okay, moment at quarter span section. Please note this point. Okay, that means I need to consider the moment at this particular point. Okay, so at this particular point, let us calculate the moment. Okay, so you already know from your basic analysis class how to calculate. Okay, I will repeat once again. So if a beam, a simply supported beam subjected to uniform distributed load of 1.11 kilonewton per meter, then its reaction at either of the supports are exactly WL by 2. That means if it is subjected to W kilonewton per meter, since it is a uniformly distributed load, okay, so the reaction at the supports are WL by 2, WL by 2. So please note this point. Okay, WL by 2 and WL, whatever the load acting, multiply by the span divided by 2. Since it is a symmetrical loading, no change in the loading pattern, no change in the loading. Okay, this 1.11 kilonewton per meter is uniformly distributed throughout the span. So hence the formula is WL by 2, WL by 2. Or otherwise, we can calculate from the basic things. So how to calculate that? So you already know that, okay, if a beam subjected to W kilonewton per meter, then how to calculate the moment? So first apply the equilibrium condition, summation V is equal to 0. That is, let me call this as RA and this as RB. So reaction at A plus reaction at B Okay, okay, minus, okay, why it is minus? Because upward reaction or upward force is positive, RA and RB is positive, and downward force, which is W, which is negative. So W into L. Why? Okay, because it is a UDL, so hence it is 0. So finally it works out to be RA plus RA, okay, plus RB, RA plus RB is equal to WL. RA plus RB is equal to WL. So let me take a moment about, that is, you are applying a second equilibrium condition. Let me take a moment about B, okay, which is equal to 0. That means algebraic sum of the moment about the support B is 0. So that is, okay, RA into L, because I'm taking a okay, the generalized diagram. So I'm considering the W kilonewton per meter is distributing throughout L meter. Okay, so RA, okay, into L. Okay, so this is the diagram which I'm going to write down. Okay, this is the supports RA and RB, and this will be the UDL W, okay, and the span is L. So this is the generalized diagram which have been considered. Okay, so now RA into L, okay, because you're taking a moment about this point, RA into L, okay, minus, okay, why it is minus? So now the conventions are, so this RA is creating a clockwise moment, hence it is positive, and coming to this, okay, W, which is the UDL into L into L by 2, okay, which is equal to 0. Okay, why it is minus? Because it is creating anti-clockwise. Therefore, RAL is equal to WL square by 2. Therefore, RA, which is workouts to be, okay, which workouts to be, so this will go to the right hand side, that is WL square by 2. And if you, okay, this L will go downwards, that is in a denominator. So this workouts to be, okay, WL by, okay, 2. So substitute this RA above here, okay, hence WL minus WL by 2. So therefore RB is also is equal to WL by 2. So like this we need to solve the problem if you don't know the concept. So otherwise, so once if you know the thing, that is, if this load is distributed uniformly throughout this, so then directly you can consider it as WL by 2, WL by 2. Okay. So now, so what is W? You already know that 1.11 is the dead load into span is 8 meter divided by 2. Here also 1.11 into 8, which works out to be 4.44 kilonewton. Okay, 4.4, okay, kilonewton. Okay, is it clear? Because W is in kilonewton per meter and L is in meter. So meter and meter will get cancelled. So the final answer you are going to obtain at this particular support is 4.44 kilonewton, and at this support is also 4.44 kilonewton. Okay, so next, let me consider the moment. Okay, so let me draw the FBD. Okay, you forget about this part. Okay, you forget about the right hand side. You consider only this part. Okay, so now let me take a moment. Okay, that is MDL is equal to about the quarter span. Okay, let me consider this support 4.44 into this distance. How this is 2 meter. So you already know if the total span is 8 meter, mid-span will become 4 meter, and half of that mid-span will become the quarter span, hence it is 2 meter. Okay, the total span is 8 meter, the quarter of that, that is 1/4 of that 8 is 2 meter. So this is the distance. So hence 4.44 into 2. So it is creating a moment. So it is creating a clockwise moment, hence it is positive. Next, coming to this, okay, force, that is 1.11. So 1.11 into 2 into 2 by 2, that is W into L by 2, and which is creating because this UDL is bending towards, okay, bending in the anti-clockwise direction, hence it is minus. Okay, so substitute this. Okay, we'll get 6.66 kilonewton meter. So like this, we need to work out for any span, if it for mid span, quarter span, or for any distance also. Okay, in the examination, they may ask for any distance. Let me calculate the stresses for 3 meter. Let me calculate the stresses for 6 meter. Like that also they may ask. Okay, the concept remains same. The only thing is this analysis part will change. Is it clear? Okay, so because till now we have been solved for mid span, so this problem we have been working out for a quarter span section. Okay, so like that, the same thing we have proceed for the live load moment. So that is, consider the same beam, okay, with 8 meter. Okay, the 8 meter. So this is the same thing. So this, the total distance of this is 8 meter. Okay, no change in this, and this will be 2 kilonewton per meter, the same thing. Okay, sorry, live load. Next, the quarter span also 2 meter, and once again we are calculating the moment, okay, here also at this particular point. Okay, so once again consider, okay, the moments. Okay, the moments are, so let me go ahead. So that is WL by 2. WL by 2 is the reactions, the same thing, because this 2 kilonewton per meter, which is distributed uniformly throughout the span, hence the reaction at either of the supports are WL by 2, WL by 2, same thing. So substitute that 2 into 8 by 2, so that is 8 kilonewton and 8 kilonewton. Okay, so now consider that 8 kilonewton towards the quarter span, that is 8 multiplied by 2, which is creating a positive moment. So that is plus 8 into 2. Next, so this UDL workouts to be 2, so which is 2 into L into, that is W into L by 2, or 2 into 2 into 2 by 2, okay, which is minus because this particular creating anti-clockwise moment. So hence, okay, 12 kilonewton meter will be the final answer. So like this, we need to work out when they are going to ask a problem, okay, in regard to the calculate the stresses for so and so span section. So now they have been asked for quarter span section. Hence, okay, instead of using a regular WL square by 8 formula, I am using this, okay, concept to calculate the dead load moment and live load moment. Okay, so in the examination, we need to be very careful, okay, while reading the problem. Okay, so next, another concepts are same, no change. So let me go ahead with the stress. Okay, that is the direct stress, P by A at the top and P by A at the bottom. Both are positive. We know that already. Okay, next, because of this eccentric pre-stressing, it will create a bending stresses, P by ZT and P by ZB. Okay, on top it is negative. We already know that. Why? Because we are inducing the pre-stressing force at the bottom, hence it is positive at the bottom and negative at the top. Substitute these dimensional parameters, okay, and get me the answer in Newton per millimeter square. That means P should be in Newton, eccentricity should be in millimeter, and Z will be in millimeter cube. So which workouts to be Newton per millimeter square. Next, coming to the self-weight stress or dead load stress, that is MD divided by Z top. Okay, so that is, we have already been told that. So this is in kilonewton meter. We want the answer in Newton per millimeter square. Hence 6.66 into 10 to the power of 6 Newton millimeter divided by the Z top, which is in millimeter cube, which workouts to be 1.37 at the top. Okay, and next 2.14 at the bottom. Why it is positive and negative? So once if it is subjected to the dead load, okay, it will create the tensile stresses at the bottom and compressive stresses at the top. So same, the live load stresses, Okay, substitute that and the answer will be 2.47 at the top and minus 3.87 at the bottom. Okay, so these are all the parameters we have been calculated, but in the problem they have been clearly asked, okay, estimate the stresses. That means what are the resultant stresses for this loading condition at transfer and at working. Okay, so as I stated, during transfer condition it will not be subjected to any type of, I can say, the external load, that is live load. Okay, so please note, during transfer condition, that means during the transfer of pre-stressing force, during the transfer of pre-stressing force, it nowhere it will be subjected to the external live load. Still it is in factory. At that particular instance, okay, this ml by zt or live load stresses will not come into the picture, leaving that, okay, substitute all other parameters, that is p by a, okay, minus, okay, 4.0, okay, plus 1.37. Okay, 2.15 minus 4 plus 1.37, which work out to be minus 0.47 Newton per millimeter square. Okay, negative, which is at the top. F inferior, okay, at the bottom, P by A, okay, 2.15 plus 6.25, okay, minus 2.14, which work out to be 6.24. So this will be your stress diagram, okay, for transfer condition. Once the beam comes to the working condition, okay, that means the beam has started to resist the external load. That means I have been placed the beam, okay, to the service load condition. Hence, okay, it will be subjected to the pre-stressing force plus dead load plus live load. So let me substitute all the parameters, so which have been calculated, and you will get 2 Newton per millimeter square at the top and 2.4 Newton per millimeter square at the bottom. Okay, and please see here a very interesting thing here. Okay, see, in the transfer condition, that means without any live load, okay, it has created a small tensile stresses at the bottom. Okay, so once at the it has been subjected to the service condition, it has been nullified. Okay, and you can see, okay, both at the top and bottom it is creating a compressive stresses. So like this, we need to calculate the resultant stresses, that is F superior and F inferior, based upon the transfer condition or a working condition for a quarter span section. So I've been solved two problems. Okay, in the last session I've been solved for midspan section, and the same problem I've been considered. Okay, and in this session I've been solved, okay, for quarter span section. Hope the concept has been clarified. Okay, so let me proceed with the next problem. So the next problem says a rectangular concrete beam. So now the cross section has been changed. 250 millimeter wide and 600 millimeter deep, is pre-stressed by means of 414 mm dia, high tensile bars located at 200 mm from the soffit of the beam. Please note down, 414 mm dia means each of 14 mm dia high tensile wires located at 200 mm from the soffit. Soffit means bottom of the beam. Full stop. If the effective stresses in the wire, so please note down, effective stresses in the wire is 700 Newton per millimeter square, comma, what is the maximum bending moment that can be applied to the section? What is the maximum bending moment that can be applied to the section without causing tension at the soffit of the beam? So please, okay, read this. Okay, is asking what is the maximum bending moment that can be applied to the section, that is for rectangular section, okay, by considering a condition that is without causing a tension at the soffit of the beam. So this is the condition they have been given. Okay, please note down, for this rectangular beam is asking the bending moment M value, okay, for a condition that is without causing any tension. That means zero at the bottom, zero stresses at the bottom. Okay, so how to proceed with the problem? So as I stated, let me calculate all the parameters, that is E, P, cross-sectional area, moment of inertia, sectional modulus, eccentricity, all those. So now, so this, in this problem, please note down. So this, okay, we need to calculate the eccentricity first, and we can go ahead with eccentricity. How? So like this type I have been worked out in the very first problem. So when the number of wires and their corresponding distance are given, when the number of wires and their corresponding distance are given, so you can calculate the centroidal distance of the wires. Okay, centroidal distance of wires. How? That is number of wires multiplied by the corresponding distance where it has been placed. Number of wires multiply the corresponding distance it has been placed from the bottom, that is 200, which has been given in the problem, divided by the number of wires, which is also same 4. So which works out to be 200 millimeter. So at 200 millimeter, I am going to induce a pre-stressing force, okay, inside the rectangular section. So hence, okay, I can calculate the eccentricity like this. Okay, so the eccentricity, as I stated, it is the distance between the centroidal axis of the section to the where exactly the pre-stressing force is induced. Okay, so the pre-stressing force is induced at 200 millimeter, and the centroidal distance of this, okay, and the centroidal distance of this section, okay, centroidal distance of this section, okay, which is y bottom or whatever the thing, which is 300. Why? Because it is a rectangular section, symmetrical section, and okay, the overall depth, okay, will be divided into 2. Okay, so hence 300 minus 200 will give you or will get you the eccentricity value as 100 millimeter. That is d by 2 minus y. D by 2 minus y, that is 300 minus 200, which is equal to 100 millimeter. That is the eccentricity value. Is it clear? Okay, next. So in the problem, they have been not been given the pre-stressing force directly. Instead of that, they have been given, okay, the stresses in the wires and their corresponding that dimension of the wires. How? So let me know the stress is 700, okay, and the cross-sectional the area of the cables is this. So how to calculate this? The pre-stressing force P is equal to, okay, area of the cable multiplied by the stress in the wires. Area of the cable multiplied by the stress. So whenever they are not going to give the pre-stressing force, instead of giving pre-stressing force in the problem, they are going to give the stress in the wires and the dimensions of the wires. So that is 4 numbers multiplied by pi by 4 into the diameter is 14 millimeter square, okay, which is the cross-sectional area of the cable, into 700 is the stress. Okay, so area of cable multiplied by the stress will give you the answer in Newton, that is 431,026.51 Newton. Okay, that is 431.026 or 02 kilonewton will be the answer. Okay, so you have been calculated E, you have been calculated pre-stressing force. Next, cross-sectional area. So cross-sectional area, okay, it's very simple. It is a rectangular section. So 250 multiplied by 600. So which is 15 into 10 to the power of 4 millimeter square. Okay, next coming to the second moment of area or moment of inertia, that is which is given by, since it is a rectangular section, I is equal to BD cube by 12. Okay, so B into overall depth. So please, okay, this is the overall depth cube by 12. That is 250 into 600 cube by 12. Since it is a rectangular section, okay, the moment of area or moment of inertia formula is BD cube by 12. Is it clear? And the answer workouts to be 4.5 to 10 to the power of 9 millimeter to the power of 4. Okay. Next, sectional modulus. Now you can see ZT and ZB are same. Why it is same? Because the Y bottom and the Y top both are same. That is the rectangular section exactly. Okay, the centroidal distance will lie at the center. So 300 and 300. Hence, I will calculate like this. So 4.5 to the power of 9 divided by 300. So which works out to be 15 into the power of 6 millimeter cube. Okay. So now let us go ahead. So now you please observe here. So nowhere they have been given the dead load, live load, all those things. Okay, so in this problem, instead of giving the dead load and the live load, what is asking directly is asking a moment. Okay, in the last problem or till today, whatever the in the session we have been worked out, they used to give the dead load, or we used to calculate the dead load by the cross-sectional dimension multiplied by the density. Okay, and they used to give the live load, and we used to calculate the corresponding dead load stresses and live load stresses. But in this particular case, he is asking the total bending moment or maximum bending moment considering both dead load and live load. Okay, that means in this particular problem, no live load, okay, they have been given. So without giving a dead load and live load, you need to calculate the bending moment REM value. How to proceed? So let me go ahead. First, calculate the direct stresses, because you know where you require any moment here or dead load stresses or dead load live load here. So P by A. So substitute that P in Newton and cross-sectional area in millimeter square, which works out to be 2.87 Newton per millimeter square. Next, bending stress, we already know P by Z, okay, which is equal to, so this is 431026.51 into eccentricity is 100 millimeter divided by Z, which is in millimeter cube, which works out to be 2.87 Newton per millimeter square. So now please listen here carefully. So now you need to apply a condition that what is the maximum bending moment that can be applied to the section without causing tension at the soffit of the beam. Okay, so for that, let me apply this condition. So how this answer has been arrived, I will tell you. So first, you know that the tensile stresses at the bottom is 0. What is that? F inferior. Am I right? The resultant stresses or tensile stresses at the bottom is F inferior. So F inferior equal to okay. So you know that P by A, okay, P by A, okay, at the bottom it is positive. Next, plus P by Z, okay, at the bottom, which is positive because the bending stresses at the bottom is positive, but the moment, okay, which we are going to consider, okay, which is not positive, it is negative. Am I right? Okay, because the tensile stresses will come at the bottom. So let me rewrite this. Okay, let me
consider this. Okay, so you know the tensile stresses at the bottom is 0 and this will become so and so. So hence the formula will be rearranged into m by z, okay, which is equal to p by a plus pe by z, pe by z. Okay, so now let me know this. 2.87 is p by a and 2.87 is p by z. So substitute this. So this will work out to be 5.74. So like that, okay, we've been calculated. So next, m is equal to 5.74 Newton per millimeter square into z value is 15 into 10 to the power of 6 millimeter cube, which have already been calculated. So hence the final answer you are going to get in 86.1 into 10 to the power of 6 Newton millimeter or 86.1 kilonewton meter. So like this, we need to calculate the moment, or we are going to calculate the moment for this particular condition. So hence, we need to read the condition properly. So please, okay, read the condition. Okay, and please note here, okay, I've been consider or calculating the moment. Okay, so this 86.1 kilonewton meter, which comprises of both dead load and live load moment. Please note, I have not considered separately. Hence, I've been generalized to m. I've been generalized to term m. Okay, so this is the way we are going to work out the problem. This is the way we are going to work out the problem. Okay, they have been asked what is the maximum bending moment that can be applied by considering a condition called tension at the or without causing. See, in the last cases I used to give 0. Now you can see without causing tension, that means which implies 0. Without causing tension, which implies 0. Okay, so tension means stresses at the bottom means F inferior. So like this we need to think and act. Okay, so this is regarding the problem. Hope the concept has been clarified. So let us go ahead with one more problem. Okay, now the next problem says a PSC beam of inverted T section. A PSC beam of inverted T section has the following dimension, whose rib dimension is 300 into 900, whose flange dimension is 300 into 600. Okay, these are all the dimensions. Rib, or I can say web, both are same. Rib or web. Okay, next. And it is an inverted T section. Please note this point. The beam is simply supported over a span of 15 meter, full stop. The beam is simply supported over a span of 15 meter, full stop. The beam is post-tensioned with a 3 Freycinet cables. The beam is post-tensioned with a 3 Freycinet cables. Okay, 3 cables they have been put, and each cable contain 12 wires of 7 mm dia. I think I have been defined these things. If all the wires are twisted and bind together, it will form a cable. Here also in the cable they have been put all the 12. That means one cable comprises of 12 wires. One cable comprises of 12 wires, each wire of 7 mm dia. Like that another two cable are placed. Okay, or another two cables are okay, or another wires are put into another two cables. And these 3 cables are placed at 150 mm from the soffit at mid-span. Full stop. If the initial pre-stress is 1 kilonewton per millimeter square, comma, calculate the maximum uniformly distributed load that it can carry if maximum compressive stress in concrete is limited to 15 megapascal and tensile stresses is limited to 1 megapascal. I will repeat. We need to calculate the maximum uniformly distributed load that it can carry if maximum compressive stress in concrete is limited to 15 megapascal and tensile stress is limited to 1 megapascal. Okay, so apart from this, they have been given a one more condition. Okay, that is assume 15% loss of pre-stress. So please note down. So this is a very important. So the loss has been encountered in the inverted T section. The loss encountered in the inverted T section is 15%. By considering this 15% loss, calculate the stresses. Okay, how? Let us proceed. So now let me draw the inverted T section. So you know that the flange dimension is 600 and 300, which they have been given, and the rib dimension or web dimension is okay. 300 is the width and 900 is the depth. Okay, 300 is the width and 900 is the depth. Okay, so next is, and also okay, these three cables, they have been placed. You can see the three cables have been placed at the midspan. Okay, the midspan means 150 mm from the bottom of the beam. See here, they have been mentioned, placed at 150 mm from the soffit at midspan. So exactly at midspan have been placed. And each cable comprises of 12 numbers of wires, each of 7 mm dia. Is it clear? Next, now they have been given one condition, that is the maximum compressive stresses 15 megapascal, which is at the top, that is F superior, and tensile stresses is limited to 1 megapascal at the bottom. Okay, so this is the thing they have been given. So by considering this stresses at top and bottom, calculate the okay UDL. Please note here, what is the difference between the last problem and this problem? See, in the last session, sorry, in the last problem, okay, I have been worked out a problem, okay, to calculate, or a problem will be asked in such a way that we need to calculate the, okay, that is moment by considering the stresses at the bottom 0. Now calculate the UDL. Calculate the UDL. That is, we need to calculate the loads, that is dead or live load. Okay, not dead load, sorry, live load. So what maximum UDL this inverted T beam can carry if F superior and F inferior are given. Is it clear? Is it clear? So in the last session we used to solve, or in the first problem which have been solved in the this particular session, they used to give all the data. We used to calculate F superior and F inferior. Okay, so which is the problem have been worked out in the this session. Okay, that is first problem, that is transfer condition and working condition. They used to give all the data, that is loads, dead load, live load, everything, and we used to calculate based upon the stresses, that is midspan, quarter span. But in this particular problem, please clearly observe, okay, F superior, that is left hand side data is given. He is asking one of the right hand side data, that is he is asking the load. Okay, so need not to be worried much. It is a very simple. Let me proceed. So you have been drawn inverted T section. Okay, so first let me calculate the pre-stressing force. Okay, so how to calculate that? Because in this particular problem, nowhere they have been given the pre-stressing force. So that is stress multiplied by the area of the cable. Stress multiplied by the area of cable. Same thing. So the stress is 1 kilonewton per millimeter square or 1000 Newton per millimeter square. Okay, let me substitute this. Coming to the area of the cable. Three numbers of cable and each comprises of 12 number of wires and each wire is 7 dia. Hence, 3 multiplied by 12 into pi by 4 into 7 square, which works out to be 1.385 into 10 to the power of 6 Newton. 1.385 into 10 to the power of 6 Newton. Okay, so like this, we need to get the pre-stressing force, or we need to solve the pre-stressing force when they are not going to give the pre-stressing force directly in the problem. Okay, next, let me go with the cross-sectional area. Cross-sectional area, or let me go with this 300 multiple. Okay, once again, divide this into two sections. So that is number one sec. Okay, so that is, this is number one and this is number two. Okay, so that is number one, that is 300 into 900. Let me substitute that, plus 600 is the width and 300 is the depth. Substitute that. So we'll get 450 into 10 to the power of 3 millimeter square. 450 into 10 to the power of 3 millimeter square. Okay, next, let me calculate the centroidal distance. So this centroidal distance very much essential for calculating the eccentricity and also for calculating the moment of inertia. Why? Because this inverted T section is not a symmetrical section. Please note down, it is not symmetrical section along this XX axis or the horizontal axis. Okay, so hence let me calculate this. So you already know the formula. Since two sections are there, A1 Y1 plus A2 Y2 divided by A1 plus A2. So that is, the area 1 is, okay, so let me consider, okay, let me consider here. Okay, you can see over there. Okay, that is, we have considered this while calculating the centroidal distance. We need to go ahead with the reference axis, the same thing which I am going to write here, RA. Okay, so let me consider the first 300 into 900. Okay, that is your A1. Okay, what about Y1? Let me mark that Y1, whose Y1 distance is, this is, okay, this is your Y1 distance. So this distance works out to be the Y1. Why? Okay, because the Y1 distance, okay, we need to measure up to the reference axis. That is 900 divided by 2, which is work out to be 450. Okay, for a rectangle, but we need to measure till reference axis 450 plus 300, which work out to be 750. Okay, I will repeat. 900 is the overall depth, which is the of the first section. So which divides exactly, because the neutral axis will lie exactly at the center. Therefore, 900 divided by 2, 450. Okay, we need to consider up to the reference axis, hence plus 300, which is 750. Like that, A2 600 into 300 and Y2 will be this thing. So this will be your Y2. Okay, so which is Y2. So which is, okay, which is 300 by 2, that is 150 divided by A1 plus A2. Okay, so that is 450 10 to the power of 3, which we already been worked out. So by substituting this, you will get y bottom. So you have been measured the centroidal axis from the bottom as 510 millimeter. So I have been marked here. Please, you can see y bottom is 510 millimeter. Therefore, y top. What is the y top? How to calculate y top? Therefore, overall depth, that is 900 plus 300. So 1200 minus y bottom will get you the y top, that is 690 millimeter. Okay, I will repeat. 1200 is the overall dimension minus calculated central distance 510, which works out to be 690 millimeter. Is it clear? Fine. So that is okay, 690 millimeter. Now let me go ahead with this eccentricity. How to calculate eccentricity? Okay, so we already know this. Okay, what is the distance? 510 millimeter. Okay, and next in the problem they have been given the centroidal distance of the wires. Okay, that is 150, and this is the centroidal distance of the section. Okay, therefore 510 millimeter minus 150 millimeter will get you the eccentricity value as 360 millimeter. So please note this. 510 minus 150, which works out to be 360 millimeter. Is it clear? Fine. So you can see here I've been solved. Okay, that is the distance between where I've induced the pre-stressing force to the distance the centroidal axis of the section. Okay, next, moment of inertia of the second moment of area, same thing. Moment of inertia of the first section plus moment of inertia of the second section, that is I1 xx plus a1 into y1 minus y bar whole square. Next, I2 xx plus a2 into y2 minus y bar. Same thing, you already know what is the moment of inertia of the first section, that is bd cube by 12, 300 into 900 cube by 12 plus area of the first section 300 into 900 multiply by y1 minus y bar. So y1 you already been calculated for the first section, 750 minus y bottom 510 whole square plus moment of inertia of the second section, that is this one, 600. Okay, be careful, this is the width and this is the depth. Okay, so 600 into 300 cube by 12 plus 600 into 300 into y2 we already been calculated, 150 minus y bottom square 510. So like this we need to calculate all the entities and you will get a final answer 5.85 into 10 to the power of 10 millimeter to the power of 4. Okay, next, work out the ZT and ZB because I have been calculating the ZT and ZB separately. Why? Because it is not a symmetrical section. Therefore, Y top and Y bottom we need to calculate separately. Therefore, substitute the moment of inertia here. Y top we already know 690, which works out to be 84.782 into 10 to the power of 6 millimeter cube. So please be careful with the units in which we are going to substitute. Next, moment of inertia divided by y bottom, which works out to be 114.71 into 10 to the power of 6 millimeter cube. So eccentricity we already been calculated. Now comes to the dead load of the beam. So we already know cross-sectional area multiplied by the density. Okay, because in the problem is asking the live load, but dead load we can easily calculate. So therefore, cross-sectional area we already been calculated, that is 415 to 10 to the power of 3 millimeter square, which I am going to substitute here. But this should be converted to meter square. Therefore, divide this divided by 10 to the power of 6 into density of concrete 24 kilonewton per meter cube. So which works out to be 10.8 kilonewton per meter. So this is your WD. So please note down, this is your WD. Okay, so already been told, instead of considering it as a WG and all, please consider it as WD or WDL. Okay, and the next, immediately you can calculate the dead load moment. So please note down, nowhere in the problem they have been mentioned it as to calculate the stresses or UDL at mid span, quarter span, whatever. So unless otherwise specified, that means if they are not going to mention anything in the problem, so you need to calculate the stresses, okay, or moment at mid-span only. So hence WD into L square by 8, which works out to be 303.75 kilonewton meter. Is it clear? Fine. So now we have calculated all the entities which we require to calculate the final answer. So now let me proceed. So now, as I stated, F superior and F inferior condition is given. You need to calculate the maximum UDL for this condition and for this condition. How? Let me proceed. So let me go. If the permissible stresses or maximum stresses 15 MPa is given or compressive stresses is given, that means compression will be created at the top. F superior compression, that is F superior is equal to So please note down. C have been indicated with a star mark 0.85 into P. So till now we have not come across this condition or situation. What is this 0.85? Please note down, while if substituting these entities or while writing down this formula or while immediately writing down the formula or while after writing the formula, please go to the problem and observe whether they have been given the loss of pre-stress or not. So in this particular problem, they have been given the 15% loss. By considering the 15% loss, the net pre-stressing force is only 85 or 85%. Hence, okay, substitute or multiply 0.85. If it is 20, you need to go with 0.80. So therefore, 0.85 into P divided by cross-sectional area, okay, minus, okay, why it is minus? Please think, bending stresses at the top, is negative because I am going to induce the cable or pre-stressing force at the bottom. So 0.85 into P into E divided by ZT plus MD divided by ZT plus ML divided by ZT. Is it clear? Okay, so now please observe. So wherever the pre-stressing force will come, at that you need to multiply this entity, that is 0.85. So now please observe here I have written, okay, so this is that then pattern. Okay, once it has been subjected, so this will be in the compression state at the top and tension state at the bottom. So let me substitute. So the permissible stresses at the top, that is compression, is 15, which is equal to, substitute everything, all the entities, okay, and calculate the ML value. Okay, calculate the ML value. And please be careful, okay, while substituting these entities, be careful with the units. Always this unit should be in Newton or millimeter square. Okay, so Newton or millimeters. So these are all the entities it should be. So you will get the final answer as 1169.22 into the power of 6 Newton millimeter or 1169.22 kilonewton meter, because finally we are going to express the answer in kilonewton meter. Like that, you apply the same thing for tensile stresses. Okay, the tensile stresses occurs at the bottom is 1 MPa. So you already know that it should be minus 1 MPa. So let me write down that. F inferior is equal to 0.85 once again. Okay, so whenever the beam subjected to the external loading condition, this loss of pre-stress will come into the picture. So 0.85 into P by A plus, why it is plus? At the bottom, you already know the bending stress will be positive. Next, minus MD by ZB and minus ML. So please be careful with this. Z bottom. Okay, and this is Z top, because Z top and Z bottom are not same. In a array, if you substitute it as Z top, whole problem, that means the final answer will be wrong. So please be careful, because clearly they are mentioning F inferior or bottom. So substitute that minus 1. Why it is minus? Because it is a tensile stress which we are going to consider as negative, and substitute all the entities. Okay, be careful while substituting, and you will get the final answer 534.86 into 10 to the power of 6 Newton millimeter. So which workouts to be 534.86 kilonewton meter. So in these two moments, consider the least value. Okay, so the least value I'm going to consider in this least value is 534.86. Okay, so how to calculate that? So once if the moment is known, how to calculate this WL or WLL, you already know that. Okay, using a formula, ML is equal to WL into L square. Why I have used this formula? Why not other formula? Because this formula holds good for midspan section unless otherwise specified. Okay, so this formula holds good for midspan section, or we need to go ahead with midspan. So hence WL is equal to, substitute this MQ, that is or ML into 8 divided by L square, which workouts to be 19 kilonewton per meter. So please note this. Okay, so like this we need to solve the problem. Okay, so we need to be very thoroughly, or we need to observe this condition. So we need to observe this condition. So calculate the maximum UDL it can carry, limited to 15 MPa, and tensile stresses limited to so and so. So you need to observe these things, and then you need to proceed. Okay, so these are the things which I wanted to discuss in this session. So with this, I am going to end the session of this particular session. So we will continue or work out few more problems on stress concept. Okay, so in this particular session, I have been solved 3 problems. So hope the concept has been clear. Okay, so if any doubts arises, you can contact me. So with this, I am going to end the session of today. Thank you.